And welcome to another video. Today we're going to be looking at the marginal distribution function theorem. So what's the claim? The claim is that let x be some n-dimensional random vector and fx be the associated distribution function. Then, for each n-dimensional real vector x, it holds that the limit as xn approaches infinity for the distribution function fx at the point x, which we can write out as x1 ... xn, is equal to the distribution function of the random variable, which matches exactly the random variable x, except it has one fewer entry, right? So x1 to xn minus 1. And here we have the same. Now, how do we go about proving this? The proof is actually quite simple, especially after a semester of measure theory. Well, the core of the proof is using Heine theorem. We also let yk be a sequence, yk iterates through 1 to infinity, and let it be any sequence which satisfies our requirement from the assumptions, meaning let it be any sequence such that the limit as k approaches infinity of yk be infinity. To note, 1, we denote b to be the following intersection, so it's an intersection ranging through 1 to n minus 1, where n is fixed, of the following sets. And of course we know that this is a shorthand. This is capital X, so this is our random variable. So it's a set of all those elements from omega, such that they satisfy this for the random variable xi for each I. Okay, then we have bk, which is equal to the intersection ranging through 1 to n minus 1 of the same set, with the main difference being that we intersect it with the set like so. And finally, we define the third set, dk, to be the following union. So it's the union where we have some L iterating through k to infinity of the sets BL complement, and the whole thing is complemented. Now, the dk set may seem a little bit fuzzy, so perhaps a picture would be in order. So suppose that k is equal to 1. So for k equal to 1, we will have some set b1, and only this, and then this will be simply the set itself, right? Because we will have its complement, and then the complement of the complement, which is the set itself. Nothing much interesting. Suppose that we had k equal to 2. And then we will have the union of the complements of these two sets, and then the complement of it as well. So the unison of the union of the complement would be something like this, and then its own complement then is their intersection. And we could go on like this by analogy. Now, this isn't exactly right, because of course we have an infinite union, right? So this admittedly isn't the best way of showing this. But one thing that I intended to demonstrate, and I did, is that the more sets we consider in the union, the smaller the total outcome will be. Meaning, as k approaches infinity, we will have fewer and fewer balls involved. And as such, the actual total area will grow. And that's a very important observation. Now, we arrive at the following inclusions. We have that for each k, dk is a subset of bk, and that itself will be a subset of b, which is equal to the union of k ranging through 1 to infinity bk. Why is this true? Well, because dk is a sort of intersection, but it will always have more balls involved than bk does, and as such it will be always smaller. And why bk is a subset of b is obvious, because it is the same set but intersected with some other set. So it's either the same or it's smaller, and this is by definition. But continuing with what I said earlier, we observe that dk actually converges up to b, or I think it's also called converges in the mean to b. Now, there are two ways of explaining this. The formal one, which I won't do here because I don't think it's necessary, is to formally write out BLs according to their definition here, do some set theory algebra, and using De Morgan's rules to obtain something from which it will be obvious that it converges up to B up here. Or the more intuitive way of thinking about it, or less informal, is to say that, okay, as k approaches infinity, this is getting larger and larger. The intersections that we do get smaller and smaller. We eventually get a whole set. And as k approaches infinity, the BLs with which we are dealing here, for them, the k also approaches infinity. Right? So here the yk goes to infinity. We know that as k approaches infinity, yk approaches infinity from up here. So this will be just equal to b. Right? So in the end, it will be just some intersection of something that looks more and more like b. So eventually it will be b. Right, that's the informal way of looking at it. Formally, you could write it out using De Morgan's rules and some other juicy tactics, and it would be obvious. Now, we know that p is a continuous function, so since probability is a continuous function, and here it is when Heine theorem comes into play, continuous function. The limit as k approaches infinity of p of dk is equal to p of b from up here and from the reasoning I had used earlier. Also, since p is monotonic as a probability, it holds that p of dk is smaller than p of bk is smaller than p of b. Yeah, it follows from the monotonicity of p and this sequence of, this series of is a subset of operators. Well, this is all nice, but then it must hold that the limit as k approaches infinity of p of bk must be equal to p of b. To see this, simply take the limit as k approaches infinity of this inequality, and you will get some a is smaller or equal to b is smaller or equal to a, and thus a is equal to b. And this concludes the proof.